So hi again. So this is a re-recording of the talk I gave today at the Digital Music Research Network workshop entitled Generating Audio Mosaics with Particle Smoothing. So today I will describe how to infer sampler parameters based on particle smoothing to make a kind of imitation or accompaniment signal. And I will talk a bit about the motivation that led me to this kind of design. I will roughly outline the method, and I will play some examples and give some remarks. So this is the main overview. So we will have a system that takes audio music as input and has it as output. And first, the audio or music will be described by perceptual descriptors. Here, these are filter banks. Then there will be an inference box, which will be the main focus for today, for this talk. Then out of that are going to come per frame controls, which directs the sampler, which file it's sampling from, what's the source position, what's the transposition or tape speed, and some gain. And this will be sort of directly implemented by the synthesis. So previous systems that I built in, there was always at least a global grid for finding the best matches. But actually, once you have the grid, it tended to slip into many different aspects of the design. And this has a performance cost as well. If you sort of infer a sequence of grid points, then maybe you want it. You want to interpolate them, so then you have a smooth sequence. And then I'll talk about this in relation to dynamic programming, which is basically an important grid optimization method. So if we assume, anytime if we have a state space that's completely discrete, like it consists of these points, then there's a special method we can apply. So it takes advantage of this structure, this trellis structure, and it can actually give us in a sense, the optimal path. So we compare this to the sort of the grid that we actually are using when we're sampling. So in this case, we have uniform hop size in the source positions that we can sample, and we also have a uniform difference in the transposition or the tape speed. But of course, depending on the tape speed, the source sort of evolves forward at different rates. So in fact, most of the results of these input frames will be off of the grid, so these antecedents, and so it's a kind of mismatch especially for the sampling application. So in particular, if we use this kind of dynamic programming path decoding method to infer a sequence, then and we synthesize it naively, then in fact we will get this kind of phasiness that's caused by overlap of samples with different phase contexts. And so actually it's quite easy to hear.
Wasp, yacht.
So another issue with this method, if you want to do inference over a large database, is that this method has a quadratic complexity in the size of the state space, which of course includes the size of the source database. So it's not so feasible. So bigger questions are sort of, what are some ways that I can infer, optimize, estimate a constrained function state sequence in a continuous state space, so in an efficient way for a large database, etc. So the idea of the method is tracking things that don't exist. So we want to kind of hallucinate. So when we have this target signal, we want to imagine that a random sampling process has produced this output. So and this this method, I will use a single random sampler that's always turned on. And then I will use a method called particle smoothing, which will basically simulate random sampling tracks. We'll differentially weight them as far as they fit the data, and get a distribution of the sampling tracks as output, or at least that's a description of the base method. So in general, particle filters are a way to represent distributions, but instead of this a parametric representation like this Gaussian over here on the left, it represents a distribution as a collection of point masses, and this allows you to deal naturally with nonlinearity and also multimodality. Like here, for example, this looks like it could be a bimodal distribution. Of course, it has a cost. I mean, you have to sample more. It's not as efficient. And so so normally when we do particle filtering and recursive estimation in general, we have a series of operators. So one is just the initial state distribution. Another is a kind of dynamics distribution, which just covers how the state evolves forward in time. Another is a likelihood distribution, which measures the match of the observation and the states that you're estimating. And the last, maybe it's the most important for particle filtering and smoothing, is it's an importance distribution. This sort of embodies a strategy that you're going to use to try to find interesting states. And so actually this is a procedural part. So actually this is actually you put in functions that tell you how to sort of more efficiently draw the interesting states that you're looking for. And so here I'm going to explain a little bit about this particular model that I used to synthesize, which here it's monophonic sampling with exact resampling. So exact resampling just means that the tape position always evolves forward exactly with the tape speed, so there's no phasiness. And I mean, we can see from this picture that it's in certain points the sampler is jumping. It's jumping from to different points in the tape, and that's a feature of the model. So to go over the operators then, we have an initial distribution that's basically uniform over the files and over the source position, and we prefer less absolute transposition. I mean, less transformation, basically, less change in speed from the original speed. And for the dynamics distribution, we always have a random chance of jumping from the current state to some other position on the tape, and also to some other transposition. So otherwise, we make some local change to the transposition, and then this source position evolves deterministically. So according to the previous and current transposition, so it's exact resampling. And then the likelihood distribution is pretty simple. It's just based on a sum of squared distance of these filter bank distributions with the prediction. And the importance distribution, of course, this is where you have various strategies to try to sample more efficiently. So two ideas that I've tried are sort of, given the current state, try to find the best transposition for the observation, and the other one is sort of building an approximate nearest neighbors index and finding the best global state for the observation, and then jumping to that if you're jumping. So, and the algorithm, so this is for one time step, is actually very simple. I won't go into it in detail here, but one thing that's nice about this algorithm is that it's simple, And of course, it's multi-purpose. I mean, this basic algorithm works for different models and different importance distribution, different strategies. And so, yeah, I mean, it's cool that you can sort of program this as an engine and sort of use it in a multi-purpose way, even as you're refining your models. So then, after executing this process for all the time steps, you end up with a distribution of correlated sample paths. And so here is just one depicted. And so, I mean, in theory, these could be sort of independent sampling paths, but in fact they're not. And this is a known limitation of this method. And so, in fact, sort of at the end time that of the sequence you're generating, you have a lot of diversity, but because of the resampling process, most of the paths derive from very few sampling paths in the beginning of time, and this is because the algorithm sort of weeds out sampling paths, or it only picks the ones that are higher probability, and so actually this leaves very little diversity for the beginning. And so for the moment, we're just picking the highest weighted path, which is kind of an estimation of the likelihood ratio, and we're synthesizing it. And I can play 2 examples just to show what they sound like. So first is just using a single source for synthesis, and I'm gonna use a target signal that's it's from Debussy's Gratis ad Parnassum, and it's just a quick piano piece. And so I have a source that's from a Boccherini Minuet. It's violin. This is a very short sample. And here, so I'm playing I'm going to play the generated audio as along with a mix, just so you can hear the similarity. And for this last example, I have the same target, but I have a mix of different sounds.
Hearing impairments or damage caused to you from excessive exposure to this sound.
Gin, zing, gin, wasp, yacht.
So some final remarks. So this was a demonstrative example of using SIR smoothing for synthesis. And it's a best effort approach that scales linearly with free parameter n. And in fact, in the default, in the sort of the default importance distribution, in fact, it has no dependence on the size of the source database at all. But of course, if you use an index, of course, then it will have some effort dependence on the size of the database. And it returns a cluster of similar variations as solutions. Yeah, that's it. So if you had questions, then you would ask them at this point. And if you have some virtual questions from the internet, then I'm happy to field them. So thank you very much for your attention.